Hi, it's time for another math easy solution to discuss further into the applied project, how fast does a tank drain, and now go over question 3 of this applied project video series. In my earlier videos I went over questions 1 and 2 as well as discussed further recap on this applied project, so make sure to watch those videos to get familiar, because with this project I'm not going to go in too much detail on the recap, but instead jump straight into question 3. So question 3 states, in many parts of the world the water for sprinkler systems in large hotels and hospitals is supplied by gravity from cylindrical tanks on or near the roofs of buildings. So if you go outside in your city or town, you might be able to see some of these large tanks of water, and yeah, that's probably what they're used for. So let's say, suppose that we have such a tank and it has a radius of 10 feet and the diameter of the outlet is 2.5 inches. And one of the types of problems that an engineer might face is, for example, let's say that an engineer has to guarantee that the water pressure will be at least 2,160 pounds per foot squared for a period of 10 minutes. And reason for this is, for example, if a fire happens, the electrical system might fail and it could take up to 10 minutes for the emergency generator and fire pump to be activated. So in other words, an engineer has to guarantee that the water pressure will be high enough to serve as a let's say a backup water pressure on a water supply in case of an emergency. And so the requirement is, let's say, 10 minutes. So for 10 minutes you need to have this water pressure, assuming that would be adequate for an emergency, as an emergency water supply. So the question here we're asked to find is, what height should the engineer specify for the tank in order to make such a guarantee? And also we're told, use the fact that the water pressure at a depth of d feet is P equals 62.5 times d, the depth of the water. And to get a recap on this water pressure, or hydrostatic water pressure and force, watch my earlier video, applications of integrals, hydrostatic pressure and force. And I'll put that link in the video link in the description below. Yeah, so make sure to check that out. It's a pretty useful video. So let's go ahead and start solving this problem. So first thing we're going to do is draw what we have. So what we're told, it's a cylindrical tank, radius of 10 feet, and the diameter of the outlet is 2.5 inches. So let's draw this cylindrical tank out like that. And let's draw a dashed line like that. So we have radius of, this is r equals to 10 feet. We're also told here that it has an outlet at the bottom. Let's just say it's at the bottom or wherever near the bottom. And this diameter, we'll call it d, and we'll call do for the outlet. And this equals 2.5 inches. So the units are different here, just to make a note. So what we were asked to find is the height of this tank. So we want to know what the height is here. So let's say we'll call this HT for H for height of tank. And this equals to, let's assume it's filled with water initially, we'll call H at when time is equal to 0. Also put a capital here for tank, H tank. So little t for time. This one just means for tank. So H, I'll just write tank. So H, the height of the tank is basically equal to the height when the height of the water at time equals 0, assuming it's completely filled with water. And this also equals to H0 right here. Yeah, same thing as right in here. We'll get to the units in a bit because we have minutes here, but I'll show you in a bit that we're going to be dealing with seconds instead. So the requirement that we have to meet is this right here. So what does this mean exactly? Let's just say that we have this emergency, or during an emergency the water, let's say it's filled, and then we are going to start taking water out. So let's say, and again we're using gravity, so we open outlet, it goes down. So after after a certain time we get a water level like this. I'll draw this in dashed line across. Yeah, okay, I don't know what that pop-up was. But anyway, so we have something like this, and this, let's just draw a buoy to indicate that's the water. So after t time, after a certain amount of time in seconds, we have h of t. So this is the water height after a certain amount of time when we start taking water out. Now the depth of water is, well, that's just from the water level downward. So this is our d depth, like that. And now if we were to graph this pressure out, so the pressure here, the pressure graph, so we're given this formula 62.5 times d, and let's draw a line like this. This is our depth plot, and we're going to draw a pressure graph like that. So we have the axis here, pressure, and this is depth following along with this depth line across like that. So the formula is just a linear 62.5 times d, so it's just going to be a straight line like that, where this right here is just equal to 62.5 times it by d. I'll spell 60.5 d. And yeah, just for completeness, this has units of pounds per foot squared. That's this pressure formula. Yeah, especially because we're given, yeah, this right here, pounds per foot squared, that pressure, and also if you see my earlier video, this is the units for this imperial units or imperial formula for the pressure. So we have that. And as you can see, the pressure is increasing as you go down in depth. So what we're going to assume is that this water pressure that has to be at least this, we'll assume that's at the outlet. That's what I'm just going to make it. That's what I assume that the project is saying, at the outlet. In fact, it is actually. So at the outlet. So that's at this point right here, or at the very bottom of this graph right here, or of this tank. So what that means is this line from here to here. Actually, here I just moved everything around to make it a bit neater. So we have up to this line. So this pressure right here is going to be, yeah, this P, it's actually going to be a function of time. Well, this is all a function of time because it goes down, the pressure changes. But this is going to be, well, the depth is equal to this height now. So that's at the very bottom. So this equals to 62.5 times it by h of t. Yeah, and here I just moved the units blob right there. Just put that there. Yeah, so basically the water pressure at the bottom of the tank is going to be just 62.5 times the height of the water at any given time. And now before I get to the question or the condition we have to meet, we're dealing with time right here. I just want to make ensure that the units are correct. So recall from my earlier video that this 62, or this pressure formula, is actually equal to mass density times it by gravity times it by d, which equals to, in US customary units, it's used actually for, yeah, using the weight density as I explained before. So rho times it by d. No, actually this is the delta. That's the Greek symbol delta. This is rho. So we have rho times g times d equals this, where this equals to 62.5. This is pounds per foot cubed. So it's a weight density, pounds is a unit of weight, and then so basically this rho is equal to this delta is equal to rho times g, where g is gravity, acceleration due to gravity, and that equals to, we'll use 32 feet per second squared. So we're dealing with seconds right here. So basically I'll just write that down. Use units. We're going to use feet for this whole question. We'll use units of feet and seconds. So instead of minutes, and instead of minutes and inches, because we're given 10 minutes, but we're going to do seconds, and here we're going to change this to feet, because again we're dealing with everything is in feet and inches. I mean feet and seconds. And I will highlight this right there. So let's now look at what condition we need to meet. Basically, as you can see here, the bottom pressure is a function of the height right here, So after 10 minutes, we need to require that the pressure is greater than 2160 pounds per foot squared. So in other words, I'll write this down. After 10 minutes, and I'll just calculate this out. Yeah, 10 minutes is basically, we'll go 10 minutes times it by, get this into seconds. So 60 seconds is in a minute, times it by, 1 min. So we're just doing 60 times and then the minutes cancel. 60 times 10, that's just 600. So 600 seconds. So after 10 minutes or 600 seconds, the requirement we need to make is that the pressure at the bottom, P at T equals to 600. S has to equal to, 62.5 times it by the height after 10 minutes. Because as you can see, that's the pressure at the bottom. So after 10 minutes, it's going to be, the minimum pressure at the bottom we need to require because the height's decreasing. So this is H times it by 600 right here. This is H of 600 seconds. Now this is what it equals to, but we need to ensure that it's greater than or equal to 2106 pounds per foot squared. So this is our requirement right here. That the pressure after 10 minutes or 600 seconds is greater than 2160 pounds per foot squared, and that again, that's assuming it's at the outlet or at the bottom of the tank. So that's what we have right there. And if we rearrange this, so if we rearrange this, we get, and then solve for H right there, so we get H of 600 is greater than or equal to 2160, and then just divide by 62.5, 62.5. So we are given this condition right here. And now the question we need to ask is, from this condition, or the requirement that we need to meet from this condition, so we need to find the H of tank, which is, H0. So the height of the water at T equals to 0, or, assuming the tank is completely filled. If it is, then that's just at the height of the tank. So that's the height of the tank, like that. So the first thing we gotta do is, let's just find an equation for H of T. So find an equation for H of T. So that's the first thing we do. So we have to first find this, and to do that, let's just recall the Torricelli's law, or Torricelli's. I'll just scroll this up, and again, make sure to watch my question 1 video. I went over a bit on this. So Torricelli's law for drainage of water of any container, it's going to be the flow rate, or the change in volume of the liquid with time is equal to negative A times square root 2GH, where A is the area of this outlet, G is gravity, and H is the height of the water. So recall this equation, and I'll put that down, and I'll write this down. So I think let's say spell it. So Torricelli's law, and what I'm also going to do is write not just this, but recall this and volume of a cylinder formula. So volume formula. So and again, this is of the cylindrical tank. So what we have is Torricelli's law, which is dV over dt is equal to negative A times square root 2GH. And I'll get over A and G in a bit. I'll just write. And then what we also have is, and the volume of a cylinder is just V equals to pi R squared, which is the area of a cross section, times it by the height of the tank, or the cylinder. And in our case, recall that the cylinder radius is just, 10 feet, and everything we're going to be using is in feet and seconds. So what we end up having is, this equals to pi times 10 squared times h, which just equals to, this is just 100, 10 squared is 100 pi times h, and that is our v right here. Yeah, so this is what we have. And now the reason I'm writing this formula right here is because we can create a differential equation or derive a differential equation from the Torricelli's law and volume formula for the height. Because now that we have volume here, we have dv over dt, but we have the h here, we can take the derivative of this. So dv over dt of the volume formula, this just equals to, well, this is just, because again r is constant, so 100 times pi times it by, now the rate change or the derivative of h is just dh over dt in terms of time. So if we plug this inside, so we can just throw this inside here so that we have a dh over dt on the left side and the function h on the right side. So we have a differential equation. So let's throw this together. So what we end up having is 100 times pi times dh over dt is equal to, this equals to, well, negative a, because that's our dv over dt, negative a times 2gh, where, I'll write this down, where g, again, that's already, I already wrote this down, this is 32 feet per second squared, and I already had written that down for the gravity in imperial or US customary units. 32 foot squared, divided by feet, 32 foot divided by second squared, I forgot that. So we have this, and where A is equal to the area of the outlet, which is going to be pi r radius of the outlet squared. But we're given the, so first what we are given is the diameter, do equals 2.5, and it's in inches. So yeah, so first thing we'll do is let's find our RO. This equals to, well, diameter of the outlet divided by 2, half the diameter is radius. This equals to 2.5 inches divided by 2, and then we're going to change this into feet. So we're going to multiply this by, this is by 1 foot, and then in 1 foot there is 12 inches. So the inches cancel and we're left with feet, but I'm also going to write this as a fraction just to make it easier instead of putting in the calculator or dealing with decimal points. We're going to multiply the top and bottom by 2 over 2, so that we end up getting, this equals to 5 on the top, 2.5 times 2 is 5, at the bottom we have 4, and then times it by 12. It's all in feet. So 4 times 12, that's just, well, 4 times 2 is 8, and then 4 times 10 is 40, so we could add those 48. So this equals to 5 over 48, and it's in feet. So we have that, we could throw this inside. So what we end up getting all together is 100 pi dh over dt, dh over, write this neater, and then equals to negative a, equals to negative, and a is pi r, and that's just, again, that's the area of the circle or the outlet, pi r outlet, which is 5 over 48, and then this is squared, times it by square root 2g and h. 2g, h, 8, where 2, I mean, g is 32 feet per second squared, times it by h. So we have this. And now this just requires, well, simplifying. Let's cancel the pi's. Let's get to just cancel those out. So we have 100 dh over dt is equal to, well, this is negative 5 squared, 48 squared, and then we have this square root. You could write this 2 times 32 is 64, so 2, or just square root 64 and take the square root out, square root h, where this simplified further, 100 dh over dt is equal to negative 5 squared, this is 25, I mean 5 squared is 25, and here what I'm going to do is write this as 48 times 48, and the reason is because we have the 64, square root of that is just 8. So 8 times 8 is 64, and I mean 8 times 8 is 64, so we have 8 right there. That's the square root of 64. That's why this is square root of h. And the reason I'm doing this is because 8 times 6 is 48. So we could just cancel this out. Yes, 48 divided by 8 is 6. So this is 6, this is 1. What I'm also going to do is cancel this out, and this is a 1 with this. This is 4. So yeah, just divide by 25 on both sides, and in this case, divide top and bottom by 8, because 8 times 6 is 48. So what we end up all getting, and then move this 4 on this side, we get a dH over dt is equal to negative square root of h. This is just algebra I'm doing here. So 48 times it by, and we're going to have the 6, and then times it by 4, because we move this 4 at the bottom. So we have this. And now we'll just do some further algebra. 6 times 4 is equal to 24. And then what we end up having here is 48 times it by 24 times it is equal to, well, this is just multiplication. You can put this in a calculator. I'll just do it by hand. Just exercise my multiplication skills. So 4 times 8 is 32. So put the 2, carry the 3. Carry the 3 there. 4 times 4 is 16. Add the 3, that's 19. Add the 0. And then we have here 2 times 8 is 16. And then add the 1, so carry the 1. 2 times 4 is 8. Add the 1 is 9. And again, then we add this all together. Yeah, if you want to learn more about this and the proof for how to multiply by hand, if in case you never actually went over that, watch my earlier video. Put that in the link below for multiplication by hand, which is pretty interesting. The derivation for it I go over. So what we have here, add this all up, this is 2. 9 plus 6 is 15, so put the 1, carry, and put the 5, carry the 1. 9 plus 1 is 10, plus 1 is 11. So put this all in the bubble. This is just extra stuff. So what we finally get is a differential equation. dH over dt is equal to square root of h divided by 1152. So yeah, now we have this differential equation, and we also have a condition that needs to be met, which is this h of 600 is greater than 2160 divided by 62.5, and we want to solve for h of 0. So that's all what we want to do, and I'll just write that down again. So we have, and the condition h of 600 is greater than this is 62.5. So this is the condition we want to meet, and this is just a basic differential equation problem. And this is a separable equation, so we can separate the h's on the one side and the t's on the other side, and then see if we could solve this explicitly. So what we do is, this is going to be dh over square root of h. Move this over, and then move the dt's on the other side. We'll have negative, and then we'll have a negative dt over 1152. So that's how we separated them. So h is on one side, t is on the other, and then take the integral on both sides. So we can solve this. Integral of this right here, this is just a constant. Integral of dt is just t. There's a negative there, so we have negative t over 1152, and then we always have to add the integration constant. I'll call this c2, and I'll use a c1 for this integration constant. So that's just a constant. Solving this one, I'll write this a bit neater. This is equal to h to the power of negative 1 over 2 dh, an integral of this. So we add 1 to the power. That's going to be, well, h of 1 over 2, positive 1 over 2, and then divided by, well, 1 over 2, which is this power, and then plus a constant c1. And then just simplify this further. This is just square root of h divided by, well, the 2 right here. So divided by, h over 1 over 2 divided by 1 over 2, the 2 just goes on top like that. So we have a 2 square root of h plus c1. Erase this. So equating these two, we get a formula is 2h plus c1 is equal to negative t over 1152 plus c2. And now what I'm going to do is combine these constants, so we get a 2 times square root of h is equal to negative t over 1152, and then this is plus c. I'll write where c is just equal to c2 minus c1, and then those are just constants subtracting each other. That's still going to be a constant, so we'll just call that constant c. So let's solve this further. Divide both sides by 2, get rid of that. So what we end up getting is a square root of h is equal to negative t over 1152 plus c over 2. I'll put the 2 right here. So we multiply by 2 like that. And now I'm just going to again do some multiplication by hand. So 1152 multiplied by 2 is just, well, 2 times 2 is 4, 2 times 5 is 10, carry the 1. 2 times 1 is 2, carry the 1 is 3, and then 2 times 2 is, 2 times 1 is 2. So multiply that by 2, and now what I'm going to do is combine this c over 2 and write that as k, another constant. So what we end up getting is a square root of h is equal to, and then I'm going to move this over, actually I'm going to remove this here, k on this side, and then just move the negative on the other side. It's just neater like this. 2304, where k is just equal to c over 2, and this is a constant as well. So we have this, and now what I'll do is square both sides, so we get rid of the square root sign. So what we end up getting is a h is equal to k minus t over 2304, and then this is a squared like that. So that is what we want to find, or I mean that is what our formula for h is right there. And this is a formula actually of time. So h of t is equal to this, and now we got to solve for k. So we know that h of 600 is greater than or equal to 2160 divided by 62.5. So let's plug that inside. So we get a h of 600, which equals 2. Plug this inside. So k minus 600 is t, or 2304, all squared, has to be greater than or equal to 2160, 62.5. So rearrange this, so square root both sides, and then move this 600 divided by 2304 on the other side. We get a k value that equals to, or I mean it's greater than or equal to square root 2160, 62.5. You notice I'm not solving this right away, just because I'd rather do that all at the end. So we square root both sides, get rid of the square, and then move this 600 on the other side over 2304. So that is what our k value is. You could put this in a calculator, or I'll just keep it like this just because we have the exact value and I don't want to simplify any further, just because you don't need to. I'll just plug that in the calculator later. So we have the k value is this. So what we could do now is solve for h of 0, because we have the k value. So h of 0 is equal to, yeah, it's just equal to, well, k, I'll keep it like that, and then put 0 inside here, which is, yeah, so we'll have 0 over 2304 all squared. This just equals to, well, this is 0k squared. So what that means is h of 0 equals to h of tank, which equals to the height of the tank, assuming it's completely filled, and this is just squaring all this. I mean, this equals to k squared, where k squared is greater than or equal to, so the height of the tank has to be greater than or equal to, and then we plug in this whole values in there. So we get this right here, 2160 over 62.5 plus 600 over 2304, and then all squared. And now if we were to plug this into the calculator, I just put in the Google calculator, so bracket square root 2160 divided by 62.5 plus 600 divided by 2304 all squared, we get about 37.689. So I'll round this up to 37.69. So what this is roughly equal to 37.69 feet. Yeah, so that is our answer right here. So in other words, the tank, or the engineer, has to specify that the tank, assuming it's completely filled with water, the tank must be at least 37.69 feet tall. And there is our answer, like that. The arrow around there. So yeah, so there is a quick engineering example that they would use differential equations and calculus to ensure that specific conditions are met for an emergency backup water supply, which is pretty interesting stuff. And this is actually what they use. Yeah, this comes up a lot in engineering and stuff, where you actually have to put in the math like this, and this is a good example of it. So yeah, hopefully you enjoyed this video. That's all for today. Hopefully you learned, and remember, you can always download these exact notes and link below, and make sure to watch questions 1 and 2. Those are also very interesting as well. Anyways, that's all for today. Hopefully you learned, and like always, yeah, you can download all these notes and etc. Anyways, thanks for watching, and stay tuned for another Math Easy solution.